Thank you, Liz. Good morning, everybody. Welcome to the second day of the conference. I'm Angelos Katsagelos. I'm a professor here at Northwestern and a co-PI and deputy director of the Institute. So George asked me to make a short introduction. Vicky asked me to make a proper introduction. So I'll make something in between. So it's really a great pleasure to have with us today Professor George Emmanuel Karniadakis. George had an illustrious career. He is from the island of Crete in Greece. He did his undergraduate degree there, his graduate degree is at MIT. He stayed at MIT for a while and then Stanford, professor at Princeton. And since '94, he's a professor at Brown in the division of applied math and fluid dynamics, I believe. Is the center of fluid dynamics. George has received numerous awards, too many to list here, really. But notably, he's an elected member of both academies, the National Academy of Engineering and Arts and Sciences, and the Vannevar Bush Faculty Fellow. George is really credited with starting the physics-informed machine learning area in computer science. He's credited to having introduced PINs, deep nets, one of the topics of his talk today. So it's really a great pleasure to have you with us, George. Please help me welcome him.
Thank you very much for the invitation. Today, I'd like to give a sort of overview first, and then ask the question, Quo Vadimus. Anybody speak Latin here? What does Quo Vadimus mean?
Where are we going?
Where are we going? You can use it in all your talks, by the way, and in all your proposals. I found out from an Italian friend that that's a good way to intrigue people. But if you look up here, we start with the physics-informed machine learning that my group will introduce, and we have a patent. You can see a patent there, for which we have received zero money, to generalize to general intelligence. And the question is how scientific computing and computational science will benefit from that transition. And the way I thought about this field is how you can assimilate data seamlessly, not the classical data assimilation methods, with numerical methods. I've been a numerical methods developer for many years. And that is where I propose these three sort of categories where you know most of the physics, and then you just solve forward, where you know no physics at all, and then you just have a black box. And then most of the times we are somewhere in between. We know some of the physics. We need closures. We need other parts to correct the physics discrepancy in terms of gray boxes. So before I go any further, I want to kind of demystify neural networks, because the computer scientists are trying to sort of mystify it. As an applied math, we try to demystify it. So let's start with the universal function approximation, which was developed by George Saipenko, an applied math assistant professor at Tufts at the time. So it's a very, very simple idea. So you have an input X and you have an output Y in the graphic here. And then you connect these through weights. The weights are, of course, the unknowns. But basically, the theorem says that the function Y can approximate the Y quantity, can approximate the function if you can write it as a linear sum of these unknown weights times sigma, which is some function. That function has certain properties, as I explained here up on the top, times this linear argument of the input weights and some bias B. So if you think about it, this is nothing else but a Taylor series or a Fourier series and so on, just like the way we are used to, where you have some unknown coefficients W times a basis sigma. This basis sigma is not polynomial. That's what this theory, the whole theorem says, that there cannot be a polynomial basis. So in all the other methods that you know, difference finite volumes and so on, the basis is polynomial. And what's the difference here is that the basis is non-polynomial. That is in order to have convergence, as shown down here. And spaces are not vector spaces and so on. So that's a single hidden layer. But as I said, it's nothing new. It's just that the basis has to be a particular basis. Radial basis functions, if you have used, for example, will satisfy that. Now, in the last 15, 20 years, we sort of went deep because of the available GPU computing. So what happens if you have a deep neural network? Well, in the deep neural network, you can write it exactly the same thing. So again, the neural network is a function approximator, and you can write a sum of some weights, which is the weights of the last layer, because the last layer is always linear for regression, and then times a basis. What is that basis? That basis are simply functions of the last nonlinear layer, the last linear layer, and the last nonlinear layer where we apply the activation function. So there's a very nice interpretation again. It's a linear combination of superposition of some unknown weights of the last linear layer times a basis, but that basis now is computed on the fly, is not a prefabricated basis like in other methods. So in some sense, if you have data or if you have physics, automatically the basis will follow that physics and the data. So in some sense, in principle, you have the best basis and the best representation, and that's why it's a good reason to use this type of neural networks in scientific computing, okay? That's sort of the motivation. It's not like we just wanted to do something else. There is a true belief in this. Just to give you an idea, I know finite elements is not very common in astrophysics, but probably you know linear finite elements. In linear finite elements, you have these hat functions which define the trial space, but you can write that in terms of ReLU functions. ReLU is one of the sigma, one of the activation functions. Exactly. So in fact, you can prove that in 1D finite elements, and the neural network representation I show you is identical. It's exactly the same. The space is exactly the same and everything. So you can now what happens even with a single layer. Now what happens if you go to deep neural networks? For deep neural networks, for high dimensions. For high dimensions, it turns out that you have to have a deeper neural network, at least 2 hidden layers in order to show the equivalence. But the equivalence again is rigorous. So this is sort of preliminary to show that what I'm talking about here is nothing new. It's actually the same thing that we've been doing with just a different basis. I hope that's clear, and that demystifies the hype. So now, what is a pin? When we started working with this, we actually started with Gaussian process regression, which is a great tool, but you could not scale well for nonlinear problems and also for big data sizes. So we switched to neural networks for the reasons I explained, and we wanted to encode the physics, any physics. So you dial in the physics together because you don't have enough data. If you have enough data, this here on the left is enough. You have 2 inputs, let's say 2 outputs. So just have this simple term, a least square minimization of the mismatch between your predictions and target values for supervised learning. That's enough. But even for a simple experiment, a simple setup, you need 10,000 experiments. So that's where the difficulty comes in physical science, is that you don't have, but we have physics, we have conservation laws. So that's what we wanted to encode, the conservation laws there. So in the bottom, you can see another term. That term is basically the residuals of some PDE or conservation law that you're solving. So we're trying to minimize the residual, and we want to do it without a grid, without any specific grid. For those of you who've been building grids, especially for complex objects, it takes a lot of time. The code is very long and so on. So we want to do it like in a Monte Carlo fashion. So basically, we're using Monte Carlo to sample the physical space and time. So therefore, there's an immediate benefit of that. that we can do any dimensionality. In fact, we show that we beat the curse of dimensionality. We have solved equations, Fokker-Planck equations, Black-Scholes equations in 100,000 dimensions using these methods, something that people probably don't know. Another benefit of all this machinery that was developed is that all these operators here, we don't build them based on approximations because we have automatic differentiation in machine learning, which allow us to have exact neural operators, differential operators. So we use that to derive all the equations. So in principle, we have exact representation of the continuum equations by resorting to automatic differentiation. Automatic differentiation in the beginning was expensive, but now with frameworks like JAX, it's become much cheaper and very accurate. So here's an example. If you haven't seen this before, it's a Berger's equation. It's a simple equation, but has first and second order time derivatives. So imagine that you have space. So this is 1D space, minus 1 and 1, where we put boundary conditions. So these are the boundary conditions on the top and the bottom. But here I pick the problem so that this is something we teach in the classroom, but a little different, because if you look at x equals 1, x minus 1, I don't have data, I don't have boundary conditions all the time. So anybody knows how to solve that? You cannot, because it's not a well-posed problem. So that simple problem, we cannot solve in the classroom with classical methods. But here we are not actually solving an initial value or boundary value problem in the classical numerical analysis sense. What we're doing, we're solving an optimization problem, which is subject to regularization. What is the regularization here? The physics is the regularizer. I don't need to do like in Tikhonov regularization like we do. I don't need to do the L2-way decay that people in machine learning do, because the physics is the best regularizer here. I can solve that problem. And you can see here the code, there's the TensorFlow. It's a historical code now. It's 10 years ago we did this. So you define the neural network, and then you just take the derivatives to get the residuals and so on. I used to joke at that time, 10 years ago, that even professors now can write their own code. But actually, we don't need now because Claude and ChatGPT writes that code. So as you know, but 10 minutes later, not 1 semester later, 10 minutes later, a high school student will get this answer. In fact, I have a paper with a high school student, 40 pages paper on this stuff, just to demonstrate that we build it to be simple. In fact, the paper pins, which has over 17,000 citations in the last few years, it was rejected because they thought the method is very simple. So I was really, really upset, but also happy because finally I built something that is simple. I used to build very, very complicated things nobody would use. Okay, so what can you do with this which is different? Here's a paper we wrote in Science. Can you extract information from visualization, from clouds, from, this is a dye visualization. In other words, you look at this, it's a beautiful vortex street. It could be behind an island or behind any cylindrical body or bluff body, an airplane. But can you actually, by looking at this, can you extract the forces on the body? Turn a qualitative information, which is the video, so pretty. Can you convert that to quantitative information? And the answer is yes, because you can use, that's why we call it hidden fluid mechanics in a sense of hidden Markov processes. You observe auxiliary quantities, but actually you're looking for velocity and pressure, and we turn that into just using now a more complicated, as you can see up here on the right, if I find the cursor right here. So you can see what we observe, we encode it into a advection diffusion equation, and then we couple it to what we think is a model, Navier-Stokes equations, for example, with divergence constraints and so on. And then we have CFD to tell us what's the correct solution, but actually we can discover only at an arbitrary geometry where we are actually interested. We don't need to solve everywhere because I don't even need boundary conditions for this problem. So I turn a qualitative piece of information to very quantitative information, as you can see on the bottom. So that sort of generally has been used in many different contexts, but this is sort of what you can do beyond the standard numerical methods. In cosmology, I don't know much. That's why you can see I put the star right here on the very right. On your left, I like that. I'll go around later and check out what people are doing. But there's all these areas from stellar astrophysics to celestial mechanics and exoplanets where people have tried to write to see if this type of methods, which do not require a grid, it's very simple to program. The codes are about 20 lines code at most, maybe 50 lines. Can you achieve results comparable to what you have, and can you solve the inverse problems? These methods are especially good for inverse problems, to discover not just parameters, but discover missing physics, black boxes or gray boxes. So I want to highlight a couple of problems, a couple of papers I found. For example, this paper, I think it's from JPL. Early on, they were trying to find if you can do better than finite difference methods that they use in gravitational hydrodynamics. And what they found here is that in 1D and 2D, probably finite differences are faster, but in 3 dimensions, and as you increase dimensionality in the parameter space, for example, pins here would be 10 times faster. And there's several applications that you all recognize, star formation and the gravitational instabilities and so on. Here's another more ambitious application on how you can use pins for astrophysical shocks. So talking about now discontinuities, when you have finite regularity in your solutions, how do you deal with it? It is problematic, but it turns out that you have to do it right. Neural networks, people don't know that because the original theory, it was only for continuous solutions, but actually you can represent very accurately, with arbitrary accuracy, discontinuous solutions. So if you do it properly, the theorem, of course, doesn't tell you how to do it, so you have to find out how you do it. But here's a problem where they were looking at, the inverse problems, data assimilation, forward modeling. Clearly, data assimilation becomes very simple now because you don't have to. And going between forward problem and inverse problem, as you know, you have to change the code. Here, you don't change your code. You keep the same 20-line code. It's exactly the same problem. You just put the weights in front of the data term, and I will explain that, or in front of the physics term. You weigh the two, the physics and the data term. So anyway, here also they could find a huge speed up, especially for inverse problems with reasonable accuracy. Because I work on high-speed aerodynamics, I wanted to explain that you can actually do a very good job with shocks. Here on the bottom left, you can see, on your left, yes, we can see that we weight every term, the residual for the physics, then the inlet boundary conditions. Here we assume that we have Schlieren photography, which means that data, which means that the gradient of the density of rho is available. That's what Schlieren imaging does, and other. You can add any constraints here. So there are exact solutions for this expansion wave. So we can test it, and you can see what happens here. You have to tune pins a little bit. For example, in this paper here, where we're looking at that, we have to introduce adaptive activation functions. What is that? And hyperbolic activation functions. In the standard neural networks, you have one activation function for every neuron, but it doesn't have to be like that. Every neuron doesn't have to fire at the same time and in the same way. So you can actually parameterize your activation functions with a single parameter, and then you can make that as a hyperparameter. So the data or the physics will define when this, because our brain works like that, and I'll get back to this later. But right now, we use activation functions as surrogates of the voltage membrane that we have in our human neurons. That can be changed. You can make it adaptive, and that makes a big difference, as you can see here on the plots. Here is no adaptive. There's some discrepancy here. This is the perfect case. Or you can use dynamic weights. This omega 1, omega 2, you can continuously change them based on the gradients. And there's also ways of doing that, but later on I will show you how to do it. And now if you have let's say you have an oblique shock, and look at how ugly is the grid that I use, because it's not a grid, right? I sort of sprinkle points. But here I do another thing. I can decompose my domain in subdomain 1, subdomain 2, and subdomain 3, and I can treat them separately. I use this continuous Galerkin, which is basically matching the fluxes and states in these 3 domains. And I can also do it in parallel because each one of these will have a different pin sitting on a different GPU and glue them together, and you can get pretty good answers. In fact, here, if I cut through the oblique shock, you can see if you don't do anything, you get bad things. But if you actually do this domain decomposition adaptive activation function, you get 1-point shock, which is very, very crisp. Okay, so there's ways to do it. The astrophysicists have not gotten there yet, like in that paper, but eventually. Okay, so I want to tell you about what's new, because for me this is old. Now, what's new? And you will be surprised, because a lot of papers, all the citations actually, and the papers, most of them or half of them are basically to say how bad pins are. And I get a lot of that. I used to be really upset, but now I enjoy it. Because my citation index goes up. So if we go back to this equation, the Berger's equation we solved, we used to solve it with this. Like the error will be 10 to the minus 3. You can see the green line using a second order quasi-Newton method called BFGS. It's a classical method. Now, this group of astrophysicists, Ruben, Stefano, Jorge, and the boss, Joe Pons, they actually introduce a new type of optimizers. It's all about find the minima, right? In this, especially for our problems, where multi-scale, the lost landscape it looks like the Rockies or the Alps for them in Europe. So they're from Barcelona. So what they introduce is a second order optimizer, which I will explain, a self-scale optimizer. But you can see it makes a big difference. You go from 10 to the minus 3 to 10 to the minus 8 in accuracy, just by changing the optimizer and also doing second machine precision. So that's new. Now, what is this optimizer that nobody's using in machine learning? This optimizer comes from a series of papers in the 90s by Al-Bali. I have the citation on the bottom. And basically, if you know how the second order methods work, we don't actually we don't compute the Hessian. That would be very, very expensive. Instead, what we do, we recursively build the Hessian from the previous iteration and with one rank matrices like that. So what they did is they wanted to condition the Hessian better. So they introduced this sigma k here, which comes out, if you do it properly, you try to find the smallest condition number of a matrix that you will have. It turns out that all these parameters can be actually computed deterministically. So it's a very simple program. You reprogram that, and then you get these good results. They apply it to a problem in magnetospheres, in a force-free magnetic field, as you can see here, where you can decompose the magnetic field to stream functions, P and T. And then you could sort of simplify the problem. But what they wanted to show is that they can use now the pin for different boundary conditions. Instead of every time you retrain the system for different boundary conditions, they parameterize the boundary conditions here. They parameterize also the stream function. And then they train the pin using all these new parameters. So in addition to the input, you're not just doing one solution at a time, you're doing many, many solutions at a time. That's sort of the idea, sort of precursor to neural operators I will talk about. But the point I wanted to show here is that if you don't do, so what they did here, the second order optimizers, you can see that if you don't do the second order optimizer, you level off at some point because of the optimization error. So it's not enough to have a universal approximation theorem. That the approximation error is actually the smallest here. As I said, it's a very good basis. The optimization error is a big elephant. And now with the second order optimizers, you get a line like that, which is just like the finite differences, quadratic convergence. But any convergence now is realizable. So we can now go to double. Okay, so we have a paper, recent paper, it's called Optimizing the Optimizer, that is already published. And we looked at all sorts of different equations. Here I have just a few: Berger's equation, Alan-Kahn equation, Kuramoto-Zhivazinski is a very this equation here. You can see the solutions in time, how they evolve with planes, which are chaotic as you go in time. and Ginzburg-Landau instabilities. So we look at all sorts of equations because people from Google try to use their optimizer SOAP. So we could show that, in fact, the self-scale optimizer built the best optimizer released just a few months ago from Google called SOAP. Before SOAP, they had another, their best optimizer was called Shampoo. So they're very good in catchy names. I'm trying to imitate them. And another paper I want to bring to your attention for those of you who are interested in this business is this paper is FP64 is all you need. You may know the title of the attention paper. Attention is all you need. So this is floating point 64 is all you need. It's from University of Buffalo, Rethinking Failure Modes and Physics in Formed Neural Networks. That's a phrase that one of my former students now at UPenn, Paris Perdicaris, used to show that pins have lots of failure modes and he can fix them, but it turns out that double precision can fix all of this. So anyway, I want to spend 5 minutes to show you how neural networks learn, not just how, is a problem? Okay. It won't be perfect. So I want to tell you how neural networks learn. Have you ever thought about it? If I take an X-ray and I go through to a neural network, how do they learn? Like from layer to layer, what happens? And in the process also, I want to talk about attention, but attention to different parts of the domain where you have multi-scale dynamics. So I talked about the loss function, where we use these global multipliers in terms of boundary conditions and so on. And we have formulas and we can treat them as hyperparameters to find this, so you don't have to manually do it every time. But actually, it turns out that you can bring these multipliers inside. For every point that you sample, you can have one of these lambdas, these Lagrangian multipliers. So then you put attention to these yellow points, because if lambda is large, you say, okay, I have multi-scale dynamics here, but I better bring my residual close to zero. Now, when are we done? We are done when all the residuals are zero, because when the residuals are zero, there are no gradients, or the stochastic gradient descent stops. So I need basically to uniformize all my residuals. And so by bringing these lambda i's for every sampling point, I bring attention to different multi-scale regions. So that's very, very useful for the type of problems we are interested in, astrophysics and computational science in general. So the idea here is how you compute those. It turns out that you do a mini-max problem. It's sort of an adversarial training where you maximize the weights and then you minimize the whole thing. So then you guarantee that you have the minimum. So all these weights have a very simple formula. You don't have to compute gradients because you use the residual. So that's why it's called residual-based attention. So you can start from a state like that, and then you know when to exit. We never know when to exit, actually. And I'll tell you that all of you, including all my students and postdocs, don't know how to exit. You look at the loss function, it goes to a plateau and says, I better finish here. But it's not true. You have to keep going, and I'll show you theory that supports that. Okay, but I gave you a hint that I have to go from weights of lambdas, these attention weights, which are very order, deterministic numbers, to random numbers. When these weights reach random numbers, and I'll demonstrate that, then you're done. You know, are we there yet? Yes. When you, okay. So here's there's lots of things going on, but here's we're trying to solve some equation. We start with the weights which will look like this because we know the exact solution here. So eventually you will see what you get from the movie. So now you're going through this neural network. The residuals are changing. The lambdas on your left changing. Underneath, we look at the slice of lambda, so you can see all these numbers changing. And on the very left, you can see the loss functions and the error. You can see that there's nothing happening for a while. and then you start reducing the error. We haven't, even in this picture, we haven't converged yet because there's still some lambdas which are not totally random. But you can see we start from something very orderly and we go to something random. So you want to go to a chaotic stage. That's sort of when you finish. Now, I also have this plot here. If you can see something as mean signal to noise ratio, it turns out, and that's the information bottleneck theory that is attributed to the late Naftali Tishby, is since the 90s, a statistical physicist, who basically said that, he observed that if you look at the gradient of the loss and you break it up into a mean part and a fluctuating part, then mean part is decaying, and then you see it goes a plateau, it goes close to zero, and say, I'm done. But then he observed that actually the fluctuating part is the one that increases from 0 to order 1. So the fluctuations, when you go very close to minimum, all of a sudden, it's magic. All of a sudden, they become order 1. So the mean is 0 now, and we follow the mean and say, okay, we're done. But the fluctuations are, and everybody's complaining that their neural networks do not generalize. Well, they don't generalize because you need to let the fluctuations take you to places that the data wouldn't take you. In other words, at this point, you want to forget about your data. If you want generalization, and true learning means that you forget your data. You got to Chicago on Michigan Avenue, but there are lots of places to explore. Now, the randomness will allow you to go that. Okay, so the stochastic part of this process will allow you to go to other places and therefore generalize to places that you have not seen. Is that clear? That really, you really need this stochastic fluctuation. Mini batching and all these other techniques help, but basically, you're minimizing a million or trillion in the case of ChatGPT, big optimization problem. You have lots of stochasticity, and that stochasticity helps you a lot to learn things that you wouldn't because of the prompting of a question only. So you go to other places, go outside your comfort zone. So that it turns out that signal to noise ratio has a sort of a universal curve. The first part is where you fit the data. But after you defeat the data, you go through this transition zone where you get all these fluctuations. The fluctuations now dominate, and that's why you go above average. And then after a while, it's a diffusion process. So typically, somewhere here, we finish. But actually, all the learning takes place through transition and diffusion. So very few people, especially those who complain, go through that transition and into diffusion, because when you get to diffusion, you will actually start learning. So the learning problem is somewhere we never go. So that's why our neural networks don't generalize. So it's very important to go there because that's where the errors become very, very small. That's where you learn things that you don't know. And I would try that in information, it's called information bottleneck theory, where you're trying to minimize the first part of the data and maximize from the information plane somewhere in one of the hidden layers to the output to try to maximize that. So it's a mini-max problem that it turns out that you can solve actually also. So what you see here, many different equations that we solve like that, and the curves is sort of the same. You go from down, deterministically, you go up, and then you have these fluctuations, and then the fluctuations finally decay. That's where you need to finish. Okay, so I talked about pins. Has been a success. This is a library we built for free. DeepXT is a million downloads. It's used a lot, not just in astronomy. Actually, NVIDIA was among the first to build a whole unit based on pins. You may have heard of the current code. They keep changing the name, but its underlying infrastructure is all pins and neural operators. So back in 2019, in Supercomputing Conference, Jensen Huang talked about physics-informed neural networks, how enhance neural networks. And so you know how he built that unit? The old-fashioned way. He hired the first author behind my back. I complained since then. A couple of Christmas ago, I got a gift from him, his favorite whiskey. I look up this Japanese whiskey. I look up the price was $100. The NVIDIA stock at the time was $300. Once I find it. Okay. So what's the problem? Why with all this euphoria is there a problem? Well, I think people have, even in the popular press, have identified that there's a huge energy divide. This is not sustainable. Only the big boys, Google and so on, and Elon Musk can pay that much money. Even the president said that they have to build a lot of new energy stations and for AI factories and so on. So clearly there's an energetic divide. If you look at the CO2 emission signature, this is GPT-2, training of GPT-2. You can see what it does to the environment compared to everything else. So there's a big CO2 signature. So you have to rethink everything. You have to say, okay, now we've done artificial neural networks, but what's different? Well, if you look at the human neuron, there's stochasticity, there's spiking. We don't have continuous data come in, there's spikes. There is connectivity is different. There's in situ memory. So the architecture is very, very different from what, if you look at the energetic divide, a human neuron is 1 million times more efficient than an artificial neuron. Not 10 times, 1 million times. And that was obvious when this master here with AlphaGo was just drinking coffee while DeepMind were feeding their reinforcement learning algorithm with 1 megabyte of power. They never advertised that, but actually it's true. So if you look at the human neuron, you have the dendrites, the branches that they take information. You have the soma, or the trunk, the action, and then you have the synaptic output. And the inputs are spikes, the delta functions. They're not functions. They're not continuous functions like we. So there's many differences. So then you close this energetic divide. But even a current system with CNN, for example, to recognize if this is a cat or a dog, it needs 250 watts to do the inference, never mind the training. So that's ridiculous. We spent, a chocolate bar is 20 watts. And 20 watts, you can do lots of multitasking, right? So you have to look at the brain. You have to go back and look at the brain, and we need to set up different types of neural networks. For example, spiking neural networks. The spiking neural networks would take inputs which are delta functions like this. They will work like the brain after there's an accumulation of a certain the total voltage, let's say, because these are electric pulses. Then you fire a neuron. So the good, and then of course there are other issues about neuromorphic chips that you can have in memory computing and so on. So what is the good thing about it is that the memory footprint is 1% of what we're doing now. The compute footprint will be probably 1,000 times or less, and that's sort of the promise. If you look at the again, the power that is needed, this is where we're heading to. There's a very steep curve. This is the Moore's law. This is what we need to do. And spiking neural networks, the trend is I will break and take you down. But also we need a higher level of abstraction. I talked about earlier how you should not need to retrain your neural network every time you do something new. Well, if you do the learning problem correctly, that's one thing. But we're talking about the high parametric spaces. We're talking about foundation models and digital twins and all that great stuff. And how do you do it? Well, here we get inspiration again from a human neuron where we have the inputs, multi-inputs, the branches, and then we have the soma or the trunk. So we built a neural network like that. You can see here on the left, we have a branch, one branch, but it can be many. And then we have the trunk, which will express something we call the operator as an output. So I'm going to change the paradigm. In 2019, we changed the paradigm. All the reviewers were from DeepMind, and even they say that it was a good idea. That instead of data in, data out, we're going to have functions in and functions out. Right? Data in, data out, function is the neural network. Now, functions in, functions out, operator is the neural network. So we want to build a neural network or two neural networks here or multiple, which working together in sync will give us an operator, a high-level abstraction. So you can change the boundary conditions, you can change even the equation, you can change the domain, you can change, and then and then you can get the solution. So we're changing the paradigm. Instead of finite dimensional space to a finite dimensional space that we've been doing so far, we go from infinite dimensional Banach spaces to infinite dimensional Banach spaces. So that would change everything, because this is also identifying the operator. Doesn't have to be a mathematical operator. It could be a Black system. So this way we identify the Black system, we identify the equations. This is a universal approximation theorem that we prove. Somebody has done actually in the 90s, the single layer, but it turns out that the single layer ran into problems of high dimensionality. But in a nutshell, this is what we have, at least for one single layer, that we have the operator G of U of Y. So I map U, so X is the input, UX is the input. So here I sample the input, and I construct one neural network that will be associated with the branch, which is here. And then this is the output. You need that because that's the basis. We talked about earlier about the basis with which we express a continuous operator in the output space. So you don't have this because you have functions. But remember, basically you think of this as learning the equation that you want to solve. So the neural network will now learn the equation, and therefore will spit out the answers. After you train it, you don't retrain again. So no matter how big the problem is, you compute in real time. You really compute in real time. So here's an example. I did that for my daughter. She hated calculus when she was in high school. So can you train at that time to the derivative, the antiderivative operator here? So basically we take U of X and map it to S of X. So can we represent this integral operator, indefinite integral operator? That's sort of pedagogical example. We take 10,000 functions. You compute this indefinite integral only at one point, not at many points. In other words, you only do one experiment for each one of these functions. And then you train the operator. After you train the operator, you can throw at it any functions. We use Gauss random fields, a space for U of t, but then more recently, we asked DeepSeek and ChatGPT and Claude to do the same thing. And a decision has to be made. What function, what space of functions would all this choose? I'm not going to take you all the details, but there's papers, the paper on the web that you can see. So I was interested to see, with this implemented deep operator network in TensorFlow to learn the antiderivative operator, choose appropriate architectures and do the same thing that we did. They didn't go back to choose Gauss random fields. They actually decided to choose their own function spaces. In a nutshell, what happens is the GPTs that they had a reasoning layer did pretty well. For example, if you look at DeepSeek R1, not DeepSeek the original version, it built a function space from polynomials, from Fourier series, and so on. Try to make it as rich as possible. The same thing with Claude 3.7 and now Claude 4. They did a good job. But if you look at these results now, it turns out that DeepSeek R1 at that time, it was much better. Here I'm showing errors in the bold. You can see the winner. DeepSeek R1 did the right job, chose the right spaces, and beat everybody else. Now Claude 4.0 also does the same thing. So you can see where we're heading, right, in terms of intelligence. Use reasoning to make a hypothesis for the spaces and then execute. They can write, of course, their own code. There's still some bugs, but they can write their own code. So deep operator has been used in astrophysics. I found this example on asteroid thermophysics challenge, where we're looking at heat transfer under various radiative boundary conditions. And again, here they modify a little bit so here's the branch, here's the trunk, and they include the squeeze and excitation layer. It's something that is used in commercial machine learning a lot for scaling up inputs and outputs. But basically, they got pretty good results. They had a huge, as you can see, huge speed up, 10,000 to 100,000 times faster than finite difference methods. So I think these are pretty good numbers with operators. I just want to say one thing about DeepONet, because again, you can see how these methods work. We used to train the trunk and the branch together with one big minimization problem. And then one of my postdocs, after he left my group, wrote a paper. He didn't include me in the paper, which was pretty smart, actually. But he said, since I have the data in supervised learning, why don't I just train the branch, which gives you the basis, and then go and do the the trunk, and that works really well. That's what this math shows. But I want to show you, going back to shocks, and we wrote this paper on Riemann O-nets, operators that solve Riemann problems, tough Riemann problems. And when I say tough, if you can see the bottom, let's see, right, the bottom right plot here is the pressure ratio is 10 billion. Okay, so these are as tough problem, Riemann problems. So the initial condition is you parameterize the strength of the shock, and then you teach the operator how to solve the Euler equations. And this is the SOD problem. You can do the Lux problem and so on. So basically, you can predict in a fraction of a second any of this, and you can get how crisp the results are, very, very accurate. The reason, if you look at that, it's the basis we built look like this. The basis pretty much follow the solution. But I want to bring your attention to this. I think it's the 10th mode in the basis of the trunk network. You can see it maintains a constant state. It has like a wavelet, a local wavelet. It's a very, very sophisticated basis that no human would come up with. So it produced the best basis to represent the most difficult of the operators, in my opinion, which is the very strong Riemann. And then also you can see the very high modes. Again, you have this Fourier or kind of, but then constant state. One of the problems in scientific computing is how you actually keep a constant state. So what I told you is this plurality of neural operators that can be represented by a human neuron or a depot net. So here you can have in the branch, you can have a graph neural network, a spiking neural network, and this same thing. So we built a Parthenon. You can see the Parthenon here with the 3 pillars of neural operators, spiking neural network, graph networks, and we propose that to the government. So we have a big DOE center that I direct on how you can use all this synergistically for different scientific computing problems. So I want to tell you a little bit about SNNs, spiking neural networks. As I said, they will bridge the energetic divide. And so you can see a ReLU function will be like this, but then working directly with spikes in, spikes out. Only when the sum of the spikes exceeds a certain threshold, this neural network will fire. So you can replace this model instead of ad hoc activation functions. So one of the difficulties with spikes is how you deal with spikes, with delta functions, because you need to take derivatives. So you have to come up with new math, how you do that, or you can try to avoid backpropagation. One of the big problems is backpropagation. Question, does backpropagation happen in our brain? What do you think? No. The answer is no. If it would happen, then I need the biggest supercomputer in my head to move around with it. So it will not have, it will not, it's not. So, but we use it. So we firstly have to abandon backpropagation. Therefore, we don't have to take these derivatives and so on. Anyway, here's an example where we actually apply depot net. You can see depot net here in the branch is a fully connected neural network, but the trunk, we made it a discrete basis using these pulses. And we implemented in the Loihi 2. It's an Intel machine. You can see how small it is, and you can get solutions. Now, how do the solutions look? The solutions don't look very good. You say there's quantized solutions, because how do you encode continuous information with spikes? That's sort of the fundamental difficulty. Of course, you can use very, very small spacing, lots of pixels, but then defeats the purpose because you don't have any gain, any computational gain. So that's where we are right now. So one thing is the other. So we're waiting for any of them to build better computers. There are all sorts of machine learning concepts that one has to use to bring down the cost. Transfer learning is, of course, one. For neural operators and digital twins, continual learning is very important. Here is an example where we solve PDEs in one domain, let's say the square domain, and we transfer it to another domain. That's very, very important, because especially for elliptic problems, the boundary conditions is all what you need. And you can see that it can be done. It can be done. We solve in the target domain. The source could be like elasticity equations in a hole, but then you can transfer 2 holes, squares, and so on. People want to do transfer learning, they go a little bit very carefully to write the paper, so they don't hit a bifurcation. But here we actually show a bifurcation. We have a diffusion reaction system, the Brusseliter equation. We train it on the limit cycle, the last example in the bottom, but then we actually predict a fixed point, okay? So we dare to go through bifurcation. Now, how do you do that? Well, it's not enough to have a regression loss. As in the paper in Nature Machine Intelligence we published, we also have to penalize something that the computer vision community is doing a lot, to penalize the conditional shift, the distribution between the source and the target. And there's a nice math that goes with that if you want to read the paper. So then, of course, there's multitasking. Gato, which was proposed by DeepMind, was able to do 600 things all at the same time, do math problems and also write poetry and so on. And the hypothesis was that for multitasking, you have synergy, right? You learn from one task to the other. Can we do that? Well, in this particular case, for us, we could learn all these different equations all at once. This is a sort of one form of equations, but we can learn all sorts of different reactions. So I don't have to retrain again. I don't have to retrain for a different geometry. I just need some very few data points to go in. And the speed up is enormous, 1,000 speed up if you have noise. So can we learn more from simple systems like a fruit fly? A fruit fly has 25,000 neurons. Okay, 25,000 neurons does all this stuff. It smells, it flies, it goes to any environment and so on. Anybody knows how many neurons we have typically? Some have more than others.
100 billion.
86 billion. 100 billion, yeah. Actually, the exact number is not debatable. I was in Oxford in May, and there was one guy there who has a very long paper about the exact number. Nobody knows the exact number, but they say 86 because it's convenient.
Round it up a bit.
Yes. So if a fruit fly can do that, I thought that they also can learn to solve PDEs because I don't have graduate students at all. And I have a big group of 30s, expensive. But with agents, we can do that anyway. So 36 so unfortunately, we couldn't teach a fruit fly how to solve PDEs, but we could get something like a vision transformer. You know what transformers are probably, but a vision transformer is something very similar where you do a domain decomposition of the image to something like that. And then you can use it and you can build a UNet. What you see here is a UNet where we embed a vision transformer here. We call it Vito. Yeah, I'm done. from the movie Godfather, but I can do a really good job if you look at comparisons with other neural operators, including DeepONet, FNO from Caltech, and so on. It gives you really good answers and very, very small size neural networks. Therefore, you reduce the energy by a huge factor. So there are ways, smart ways also to the architectures. I'm pretty much done. If you're interested in this, there's a free course at NVIDIA website, which we develop for NVIDIA. So not only, they took our stuff, then they asked us, can you develop a course for us? So we did that at the price of one whiskey bottle. So deep learning for scientists and engineers. In the course, 40 hours of video. We do all the basics. We teach all the frameworks, including JAX. And more recently, we work with MathWorks. And so if you want to use MATLAB now it works as fast as PyTorch. This is a work that one of my collaborators in the group did. And then module 2 has PDEs and operators, what I told you about. Module 3 is code, scalability. Modulus used to be, is what's called now, their library is called Physics Nemo. And then there's all sorts of course projects. Not sure if we have astrophysics projects, but then the educators can carve out things and do a course. My work is supported by Muri and also from this DOE center. And thank you very much for your attention.
So thank you. Wonderful talk. Any questions? Yes.
Thanks for the talk. For pins, can you comment on how well they work on the noise? So if you work on less than ideal data.
Yeah. They work well. Up to 10%, 15%, you don't have to do much. Mm-hmm. After that, you have to go to sort of Bayesian what we have Bayesian pins, which we have published. But more recently, in the last 2 years, we've been working with Kolmogorov-Arnold networks, and we found that cans are actually more tolerant to noise than pins. So that representation matters. But again, if you go above 15%, it's but let's say with 15% noise with cans, you will not see any change more than 1%. It's really robust, cans in that sense. Cans, the two representations are comparable, but I would give the upper hand to cans when it comes to, we call picans. Physics informed cans. To that, yeah.
And if I may, another question. You mentioned in the information bottleneck theory, there's this diffusion phase. What's driving the diffusion?
Oh, all the stochasticity that comes from the mini batching, the stochastic gradient descent, all that.
But you get generalization even in non-stochastic optimization for very large networks.
You do actually, even without mini batching.
Right.
I don't know about generalization. It depends what you call generalization. Well, the information bottleneck theory is a little bit controversial, I have to admit. But at least in the context of pins, we verified in some of the students of THP want to have their own glories, and they dispute some stuff on compression and so on. But we found that actually it works for us. The stochasticity would come from anything, actually, from noise. You just need a little bit of noise to trigger it. But there's no single problem. You saw all the examples that I had there. They all went through this diffusion phase. So in fact, the way to describe that, we have the model, and THP had a model, is kind of advection. Think of advection diffusion. So you can have a Fokker-Planck equation describe the whole model. He didn't talk about the transition itself. He called it a phase transition. With just, not this transition region that you always have.
Vicky?
There's a question. There's a question right here.
Thank you. I have a question on the diffusion phase as well. I can see how formally you should wait until you reach that phase to be sure you converge, let's say. But in practice, do you gain? I can imagine that makes it more slower.
Much slower.
Much slower. So, and then I saw the number of iterations, etc. And then, do you really gain? Are there practical problems where you gain in accuracy, for example, compared to finite differences, which is really your goal in doing pins?
Again,
so
it depends. If you want to use this just to solve a problem in the forward mode, I like spectral methods. I come from spectral methods. I will use spectral methods. But that's not the point here. The point is that you're missing some terms, like I show the boundary conditions. You're missing. So you somehow you end up doing this type of neural networks approximation. Now, if you want to solve only to fit the data, you just stay there. As soon as you see the plateau, you stay there. But we have, in the paper, we have plots where they show that the plateau, you go to the plateau, you have a loss that is flat, the curve is flat, but actually you see the error still going down, way down, orders of magnitude. So you gain in terms of accuracy. Now, your point is well taken. That will slow down the process. So then one of these numerical methods that is around will be much faster. And that's true. But again, I was addressing the issue of generalization.
Generalization and
learning.
That we're interested in that, not just driven by the data, but actually without the data.
That's right. Learning, basically, you go through two phases. In the first phase, you have the data, they guide you, you have to fit the data. So, okay, you are now in Michigan Avenue, but you stay there, or you want to go to other streets and so on. So I think that part is very important.
Yeah.
Can you speed this up? I don't know. I mean, that would be probably something that.
Would love to talk more.
Yeah. Is there a question?
Michael?
So
Reversible neural networks by construction have no information loss between input and output. So aren't they a counterexample that disproves the information bottleneck theory of generalization?
Do they generalize?
No, they generalize.
I know that I use them. I use them as just a projection. I'm not sure actually if they generalize, but you're right. There's no loss there.
I think this is much more controversial. So I think if you're going to claim information bottleneck is the key to generalization, you can get the answer for work and have no issue.
Do you know any theoretical work where they have generalization bounds for invertible neural networks?
I'm not a theorist, but I think in practice, folks are using reversible neural networks.
They use it. Yeah, they use it. I use it. I use it in I have a paper on Hamiltonian and Poisson networks, and I use it actually just to do a projection without loss. But I wouldn't say that I have seen it somewhere where they actually claim that it generalizes to something. But it could be that you don't need that diffusion stage. I mean, I didn't develop the theory.
Could be that you don't need an information bottleneck, right?
In my problems, I think I need it. I have several counterexamples where if we don't go through for fluid mechanics, if we flow in a cavity, if you don't go through that phase, you don't solve the problem right. Okay, so there's an example in that paper which I'm happy to show you.
All right. Well, we can discuss more offline.
Yes, we continue. Yes. Okay. Go for it.
Thank you for the talk, Professor. Once I heard you were developing a TPU with Google, and because you, for example, for these constraints, you use partial differentiation, right? So it's, I think, the most expensive part built into the computational graph. So first of all, how do you handle it? I mean, you use, for example, in your GitHub codes, I can see that your students always use TensorFlow to create these partial differentiation for your constraints. I mean.
Right.
And this partial differentiation is a very expensive operator. And how do you handle it? I mean, is it, I mean, you use, because I'm not sure about the architecture built inside TensorFlow, but I think they...
We don't use TensorFlow, we use JAX. We use a computational graph, JAX.
So you build this partial differentiation once and then you use it for multiple times across the batches? This is what you do?
Yeah.
Because, you know, like in PyTorch, for example, I always use the partial differentiation torch autograph facility to create again and again and again over batches. So you create once and then you use it multiple times?
Yeah, but also it depends on many problems with resample. So we don't have to have the same points and so on. You have to recompute everything.
Recompute everything again? Okay, you do the same. Another question is...
That helps also the convergence.
Oh, okay. And the second question is, your deep ONets are specifically designed for integral operators, or can I use it for example, learning differential operators as well?
No, these are mostly differential operators. Actually, for Fredholm's integrals and sort of other pseudo operators, we have even fractional operators. I have a paper on fractional operators. We use for fractional PDEs and fractional operators, but integral operators too. But it's mostly for PDEs.
For PD, so but PDEs are linear operators, right? I mean,
no.
I mean the partial differential operators.
The Navier-Stokes are not.
No, yeah. I mean, I understand your point, but for example, the first order PDE, for example, when I take
the wave, the one that I show with Vito, that's a second order wave.
Okay. So you learn these operators as well.
Yeah.
Okay. Thank you.
All right. So one last question, maybe. Yeah.
Thank you for the talk. So for the pins forward mode, even with the best optimizer, it's still order of magnitude slower than, for example, finite difference method. So could you comment on that, like what we can do to improve the speed of training of the pin?
Oh yeah. So for the, I don't know if you remember the second order optimizers, how fast they converge, sort of.
Yeah, but
the self-scale optimizers are extremely fast. So all the comparisons, the literature are only with Adams, which goes slow, and then eventually with LBFGS converts something. there's no, I think with the second order optimizers, even with in 1D, pins will beat the classical methods.
So you mean it can beat the speed of finite difference method?
Sure. Sure. So it's not just the accuracy that I was showing, but there's also the, I can show you the break again. Remember the curve, how it looked, boom, like that. It was very fast, very fast decaying.
All right. So with that, we can continue interacting with the speaker. Thank you very much again.